Good morning, class. In today's session, we'll be studying the reverse biased operation of PN junction diode and its voltage ampere characteristics, which are also called VI characteristics. In the previous session, we have seen the necessity of biasing to set up the operating point, and we have also seen the forward bias operation of PN junction diode. So in this session, we'll be studying the operation of PN junction diode and the reverse bias condition, and also the voltage ampere characteristics of PN junction diode in both forward bias as well as reverse bias conditions. Now, coming to reverse biasing, here the negative terminal of the battery is connected to the p-type material and the positive terminal of the battery is connected to the n-type material as shown in the figure. So what happens when we connect the negative terminal of the battery to the p-type material is, as we all know, in p-type material, the majority charge carriers are holes, which are positively charged. So the negative terminal of the battery pulls these holes towards the negative terminal. And similarly, the majority charge carriers in n-type material are electrons. So the positive potential of this battery pulls these electrons towards the positive terminal. And we can see that the majority charge carriers are pulled away from the junction. The majority charge carriers are pulled away from the junction. And this results in increasing of the depletion region. And this results in increase of the width of the depletion region, and the diode becomes non-conductive. And the diode becomes non-conductive. Let us see the reason why the width of the depletion region increases. Since we are connecting the negative terminal of the battery to the p-type region, what happens is the electrons are pushed into the p-type region, which recombine with the atoms over there, and they form negative ions. The negative terminal of the battery provides electrons which enter into the p-type region and recombine with the atoms present over there and form negative ions. Whereas the positive terminal of the battery pulls the electrons from the n-type. So when an electron leaves the n-type, the atom becomes a positive ion. So when an electron leaves the n-type material from an atom, the atom becomes a positive ion. Since the number of negative and positive ions are increasing, the width of the depletion region increases. The width of the depletion region increases in reverse bias condition, and thus the diode becomes non-conductive. That is, no charge carriers will flow across the junction. So this diagram over here depicts the operation of PN junction diode in reverse bias condition. So in reverse bias condition, the diode remains non-conductive and the width of the depletion region increases. But if you observe carefully, even in reverse bias condition, we do have very small amount of current called leakage current. So where does this current come from? This current comes from the flow of minority charge carriers. See, if you consider a p-type material, the minority charge carriers in p-type material will be electrons, whereas the minority charge carriers in n-type material will be holes. So the potential of the battery, what it does is it sends the charge carriers, the minority charge carriers, to move across the junction. The polarity of the battery, what it does is it allows or it flows the minority charge carriers across the junction. Since the minority charge carriers are very less in number, we get very small amount of current called leakage current. And this leakage current at normal room temperature is very, very less. Hence, it can be neglected. But with increase in room temperature, the minority charge carrier current will also increase. That is, the leakage current increases with increase in temperature. The leakage current increases with increase in temperature. As you can see here, at room temperature, which is 25 degrees centigrade, there will be negligible amount of minority carriers and hence negligible amount of leakage current. Now, if the temperature is increased, the leakage current will also get increased. See, if you consider germanium and silicon materials, germanium is very much susceptible to this changes in temperature. That is, if the temperature increases, the leakage current in germanium material will increase drastically when compared to the leakage current of a silicon material. That is why in modern electronics, silicon is the most preferred semiconductor material. So this is the reverse bias operation of PN junction diode. So in reverse bias operation, the diode becomes non-conductive and there will not be any major current flowing across the junction. There will be only very small amount of current called leakage current, which is due to the flow of minority charge carriers. And at room temperature, this leakage current is very, very small in a value, hence it can be neglected. And as the temperature increases, the leakage current increases. And germanium is most susceptible to this phenomena. That is the increase of leakage current due to increase in ambient temperature. And that is the reason why silicon is the most preferred semiconductor device in modern electronics. Now, coming to the current voltage characteristics, IV characteristics. Okay, so what does this IV characteristics tell us is we will be supplying our diode with external voltage, right? So we will be there are three major biasings: no biasing, forward biasing, and reverse biasing. So when we are applying forward biasing to our PN junction diode, what we will be doing is we will be varying the voltage value in small amount of steps, and we will be seeing the current flowing through the diode. Similarly, we will be applying reverse bias to our PN junction diode, and we will be increasing the reverse voltage in steps, and we will be seeing what amount of current is flowing through the diode. So this is called diode VI characteristics, voltage current characteristics, or they're also called as volt ampere characteristics. So as you can see here, this entire diagram depicts both the forward and reverse bias characteristics of a PN junction diode. Now let us see each of these characteristics individually. That is, first we will be seeing the forward bias characteristics, and then we will be seeing the reverse bias characteristics. Now let us move to the forward characteristics of PN junction diode. So here, let us call the voltage applied to be forward voltage VF, denoted by VF, and the current occurring due to this applied voltage is called forward current. Let us denote it by IF. And as you can see here, we'll be initially applying a voltage in terms of 0.1, 0.2, 0.3 volts, and we'll be increasing it at a step of 0.1 volts. Now, if you consider a silicon diode, you can see over here, initially when the voltage is 0, that is when the applied forward bias voltage is 0, there will be no current or negligible amount of current. And as you can see, when the voltage is increased from 0 to 0.7 volts, there is drastic increase in current. So the voltage value at which you can see drastic increase in the current value is called knee voltage. The voltage value at which we get drastic increase of current is called knee voltage. For a silicon diode, the knee voltage is 0.7 volts, whereas for a germanium diode, the knee voltage is 0.3 volts. So these are the forward characteristics of a PN junction diode. See here, the point at which the sudden increase in current occurs is called as knee voltage. For germanium, it is approximately equal to 0.3 volts, and for silicon, it is 0.7 volts. Now moving on to the reverse characteristics. So these are the reverse bias characteristics of a PN junction diode. As we have seen, when we are applying reverse bias, we have discussed that our diode becomes non-conductive. That is, it will not allow any current to flow through it. But still, we will be getting some small amount of current, which is called leakage current. And this leakage current is due to the flow of minority charge carriers. And you can see the value of leakage current is very, very small. That is less than 20 microamperes. Micro is a very, very small number, okay, for silicon, and less than 50 microamperes for germanium PN junction diode. But the important point to be noted over here is, if you keep on increasing the reverse voltage at a certain voltage value, you'll get drastic increase in the reverse current. So this drastic increase in reverse current is due to the breakage of the diode. The breakage of the diode, and that voltage is called reverse breakdown voltage. So why breakdown occurs in diode is due to two effects. One is Zener breakdown and the other is avalanche breakdown. So these two phenomena result in occurring of breakdown in PN junction diode in reverse bias condition. So these are the forward and reverse bias characteristics of PN junction diode. Now, there are some important terms that we need to concentrate on. First one is the breakdown voltage. So breakdown occurs in reverse bias condition, right? So the minimum reverse bias voltage at which the PN junction breaks down with sudden rise in reverse current is called the breakdown voltage. Knee voltage. Knee voltage occurs in forward bias. That is the forward voltage at which there will be a sudden rise in the forward current value, or when your PN junction diode start conducting is called your knee voltage. And coming to peak inverse voltage. Peak inverse voltage is, it is the maximum reverse voltage that we can apply to a PN junction diode without breaking it or without damaging it, is called peak inverse voltage. Next is maximum forward rating. Maximum forward rating is the maximum amount of current that can pass through your PN junction diode, or the maximum amount of current the PN junction diode can conduct without damaging itself is called maximum forward rating. Now, coming to maximum power rating. Maximum power rating is the maximum power that can be dissipated by PN junction diode without damaging the junction is called its maximum power rating. So whenever we buy a diode, all these values will be specified. All these values will be specified for a diode. So these are the VA characteristics of PN junction diode in forward bias and reverse bias conditions. Thank you.